We're going to go over machine learning toolkit for InterSystems IRIS. We did a co-innovation project in healthcare with them. My name is Paul Hegel. I'm a senior application developer for inland imaging. This is Sergey, and he's the sales engineer for InterSystems. We have several others that helped us on this project. We have David Paxton, who was a senior integration developer. He's sitting up front here from inland imaging. And then we had Shiao-Bin, Soong, he helped us from InterSystems, developer. And then David Lepzelter, data scientist from InterSystems. So just kind of an outline of what we're going to go over. The inland imaging group, I'm going to kind of go through what we are and the use case that we came up with that we wanted to try with machine learning. This is proof of concept that we kind of came up with for exam code mapping. And then we'll go over the different ones that we use. So we used brute force, and we'll go over fuzzy mapping with our gateway, and then text-to-vec with our gateway. And then we'll just talk about generally the ML Toolkit and just our findings and our next steps that we went with. So our IT use cases. So first, just tell you a little bit about inland imaging. We're a radiology company that in the Pacific Northwest. We have a kind of a dynamic environment with Seattle and Spokane, Richland, and Missoula, Montana. So we're across the Northwest. And we have approximately 95 radiologists and 500 plus employees. Inland serves a wide variety of clients across the Northwest in rural areas like Washington, Idaho, and Montana. So inland imaging is driven by innovation and is dedicated to improving patient care through infrastructure, technology, and tools needed to deliver the best possible care to our end outcomes. So really our radiologists are really dedicated to improving healthcare through technology. So this is kind of our inland imaging's radiology exchange to support our teleradiology services. So with our, I guess I'll go over to this one. I think most everybody can see here. So we have referring hospitals and clinics that send us orders and receive results. We have our inland imaging centers that take images and where maybe our doctors, our physicians, radiologists might work. And then we have external imaging systems that send information or images into our system just for PAC storage. What that does is it comes into InterSystems Health Connect or IRIS for Health. All of the information comes in here. We have a patient index from InterSystems, so we keep a good EMPI through that. And then what that does is it makes so we have a good solid record of the patient as it goes through to the radiology information system, the voice recognition system, and our imaging system. So what we have, we had those different areas, right? So we have to cache our images so it's closest to the radiologist. So this image routing system is used for that purpose. So we use our InterSystems to tell the router to send images to a certain cache in that region. So like if a radiologist is reading an exam for Richland, we would cache the images into that cache. So as a part of the examination records, we kind of came up with a area that we want to work on. A problem. This is our problem statement, basically to say, okay, exam code mapping is currently a manual process, so our clinical application specialists have to do that. So when we're initially setting up a new customer in our system, we have to map all of their exam codes to our gold standard exam codes. So that's a 40+ hour task for our clinicians, clinical apps people. There's an ongoing maintenance that has to occur. So we get new HL7 in that has a new exam code. We have to map that manually. So we have to send out messages to do that. So those are currently in Ensemble. We send out a message saying, hey, we got to map this exam code because it's not currently mapped. And so we have to wait for a clinical apps person to do that. If it's an ED, we have to send it in anyway. And it kind of dirties up our exam code dictionaries. So we're trying to avoid those types of things. So our vision is we'd like the system to use machine learning to do the initial mapping for the customer exam codes. And then we'd like to get like an 80 to 95% success rate so that maybe we're 5 to 10 hours of work for the clinical apps person as opposed to 40+ hours. After that, we'd like to look at doing a business process in Ensemble or interoperability as it passes through to attempt to map those new exam codes that come through. And initially, we might just send out with that notice the suggested mappings and that kind of thing. And then, just continual learning of the ML model. So as they confirm that it's good, then the model will get better, and so on. So the technologies that we wanted to start with, or we thought that would work best for us, was to use IRIS for health, using the R language. Chose that because I was working with that in SQL Server, so I wanted to kind of be in that arena, not that you have to. And then data sources. So we have a cross-reference table in our Ensemble that cross-references exam codes from customers to our gold standard. So that'll be like our data source for how it's currently mapped by humans. And then we'll have that's used to do both the inbound mapping to our gold standard and to do the outbound mapping to their exam codes. So we came up with, in this test, I gave them a customer file that just had one customer's mapping to exam codes. And so basically just kind of the process, how we look at processing the files, or our thought is that we'd like to create a rough method to map the files until we get to a 90 to 95% mapping algorithm. So we wanted to try multiple algorithms to try and get to that point. And then look to create a web front end to do mapping based on file upload. So we wouldn't do this a manual file like in a folder or something. We'd just make it so a clinical apps person could upload the file and then host an InterSystems IRIS for health and making it available in Ensemble. So I'll hand it over here to Sergey.
Hi everyone, Sergey Lukyanchik of InterSystems, and I would like to continue by going deeper into those methods that have been implemented. Maybe at times I'll be speaking some slightly specific languages. Please bear specific language of mapping science. Please bear with me. I'll try to be as explicative as possible. At least that's what we told. That's what they told me to do today. And before going into the subject, I would like to mention that this is a co-innovation project. That means that we co-innovation in the direct sense of the word, because we don't have millions of records to apply for example, a neural net that would be probably the most efficient for that task. But we are constrained to the batches of records that are being circulated by the ensemble landscape, and we have to work with the orders of probably thousands of records. That cuts us off from neural mathematics and forces us to apply, to team up different approaches that are maybe simpler in terms of their science power, but since I said team up, in the end we are able to approach a valid result. So In the course of that use case, we implemented three mechanisms. Two of them, the first one called brute force, is actually exact mapping of the input text, and the input text are the exam descriptions that Inland Imaging is receiving from its partners, from its customers, and that have to be mapped to their gold standard. The second, basic method is called fuzzy mapping. So that one is based on the R statistics mathematical modeling package fuzzy join, and we'll have a couple of words about it. In the end, we implemented a means for Inland Imaging in case they extend that set of tools from just two methods, brute force and fuzzy join, to more, for example, dictionary-based methods. And we have colleagues here that are in progress with piloting those mechanisms, that they have a effective means to compare the performance of those multiple approaches among them, to automatically select the most valid one, the most relevant one, and suggest it to the clinicians, to the users of their ensemble landscape. So with that, let me say a couple of words about the exact mapping mechanism. So what you see on those slides is exactly that. On the left side, we gave examples of the input descriptions. The input, that means that comes from our business partner, and our business partner speaks different master data language. They code it differently, and they may formulate differently their code descriptions. So in one case, well, if we have in our gold standard, for example, skull scan or something like this, though the partner may use cranial numeric imaging or similar phrase. So exact mapping is basically parsing that description into separate words. That was our implementation. Parsing into separate words all the descriptions in the reference, in the gold standard dictionary of Inland Imaging, and then identifying the words that match exactly. Very simple. The bottom line is, as long as we have an exact match among any words between the input and the reference, we count that and that count. For example, in this example, we have a space of 5 by 5. So we imagine we have not more than 5 words in the description, in reference, and then in the inputs. And in that logic, for example, in this case, we'll have a similarity of 3 from 5. In that case, 4 words matched between the input and the reference, and we have a similarity of 4 out of 5. In this case, if that's only 1, then it makes 1/5. And by running, that's why it's called brute force, by running and testing all the valid combinations, that means non-empty strings and without any special characters and so on, regular strings, we identify in our reference dictionary those terms, those gold standard terms that could be considered matches for the input terms, for the input descriptions. Fuzzy is a bit different. So fuzzy join, apart from the fact that the fuzzy join package in R suggests and makes available 6 different methods to measure what is called a fuzzy distance between the input term and the reference term against which we compare their similarity. We also make an assumption that a match can be partial, and that partiality can be measured. So that can be measured using the edit distance. So for example, if we call the edit distance the number of characters we need to change in the input string to obtain the reference string. So for example, if the difference is only 2 characters, then the distance will be 2. If we consider the maximum distance, the maximum number of characters that we in principle take into analysis as 25. So for example, if there is only 2 character difference between the input and the reference, then similarity score will be 23 out of 25. It's quite a high score. There is another approach which is slightly more detailed. I will not go into the details. For example, the Jacquard method that measures similarity in terms of in the range, by the values in the range of from 0 to 1. And the similarity you may receive as the output, probably for similar situation, as something like 0.93. So that means the 93% similarity between the input and the reference. In this case, there could be other way of measuring the distances. That can be soundex method to measure the sounding distance, or it can be any other approach which could give you a different measure. So for each of the methods that we use in the prototype, we calculate the measure that is given by the method itself. And that's why in the end we need a method agnostic means to compare the results given by each of those methods. That approach is exemplified at that slide. And what we see here, basically the thought is simple. We calculate two additional measures. One called is similarity TV, text to vector. So cross methods similarity. And we calculate a metric called humanity. So similarity, the cross method agnostic similarity is based on the package called text2vec that helps us to convert any string, the input string and the reference string, to a format of a numeric vector. And then, however, the match from the reference dictionary was obtained, regardless of the method that was applied, we can just measure, for example, the angle between those two vectors, which will tell us how similar those two texts are. We can, for example, use the cosine measure, which becomes 1 when they're parallel, the elementary math. Let's remember the school course. And if they're orthogonal, that means there's no match, then the cosine is 0. So that's how it works for text-to-vec similarity. Humanity is a little bit more tricky, and this is the probability, the P probability of that a match suggested by an algorithm, whatever it is, exact mapping or fuzzy mapping, would be obtained by humans. And with that, we go back to the fact, and that was mentioned by Paul, that currently a panel of humans is used to obtain mappings, and we have a reasonable number of those mappings to learn from. So that's what we've done. So we've trained a classification model. We have taken the models that have been done by humans for ones. We have constructed the mappings without any mapping term found as zeros. We've trained that model, and as the outcome, for example, what that slide tells us is that even if the algorithm has suggested a perfect match 1-to-1, the humanity of that match would be only 65%. Why? Because the real experts in the field, the clinicians, would very rarely enter in the dictionary that sort of matches. Okay, that's a very rare case. Most of the times, they will be suggesting something that is not exactly an exact mapping. So in these terms, using those two metrics, we are able to compare the results that are given by any specific algorithm we would put on our panel to obtain mappings. A couple of words about the actual results. So what we see here, we see in those frames, green frames, the results produced by brute force method and by the fuzzy join method. Just to give you some numbers, from the initial 101 non-mapped input exams, so we applied it first to the portion that was not mapped anywhere by the humans. We had, for example, 7 to 13 full consensus mappings. That means that the both methods, brute force and fuzzy join, suggested the same guess for the term that is being tested. And that's quite a huge percentage. I would say that doesn't mean that all the others were completely wrong. That just means the perfect matches represented up to 10% from actually the batch. For the others, we had 99, almost 100% guesses suggested by brute force. So brute force is really strong in terms of suggesting something. It will almost always find some candidate as a mapping. Fuzzy join is a little bit more capricious, so it maps from 90 to 95%, and the rest it just leaves non-mapped because it tells it's beyond the scope of my maximum distance. So I didn't find anything there, which is fine. By the same token, we've also applied the same methods to the mappings that have been done by the humans. And that was also an educative experience in the sense that we found some cases where the methods, the algorithms suggested sometimes even a more correct mapping than the humans did. But in principle, what we've done, we've taken 1,253 mapped input exams. So out of them, we've got 13 full consensus mappings. That means all the three, the gold standard here, brute force and fuzzy join, presented the same term, the same description. From 1952 to 185, we had partial consensus mappings. That means the algorithms were in agreement among them, and they were in disagreement, slight disagreement with golden standard. And again, the coverage with sort of guesswork effectuated by the algorithm was 99% for the brute force and from 90 to 95% in case of the fuzzy join. Finally, like I said, we obtained those method-independent measures. So we've calculated the method-independent similarity and humanity for the brute force approach, and the same for fuzzy join. And the results were curious in the sense that some mappings that showed greater similarity, they were less humane than their neighbors from the fuzzy join space, which were less similar but more humane. So that's the essence, and that's the interest of actually introducing such measurement before making a final decision which mapping we will suggest to the team of clinicians. So that's to give you a brief idea about how it looks and feels. This is the brute force. There is no R, no nothing. It's a pure object script. On the contrary, fuzzy join is full of R scripts. Some of the portions of the R script, R modeling script, are implemented in parallel using the force of our ensemble. In the end, the results are being written back from R context into the data table, and we expect that we'll be left with some minutes to give you a short demo, live demo of it. So just a couple of words about the tooling behind that exercise. We were using a set of extensions that we called ML Toolkit. Those are open source, publicly available extensions available through our OpenExchange marketplace. We have here today Shiao-Bin Soong, who is the developer and who endorsed myself and Edward Bibiduc, the developer of the Python stack. So Shiao-Bin is R stack, and Edward is a developer of a Python stack, to present in brief terms the architecture of the tool. Edward.
When Sergey and Paul told me I have to tell you about ML Toolkit, and I only have 5 minutes and 1 slide, I thought, hey, I'm gonna cram all the buzzwords you ever can hear in it. Okay, so let's get going. We have this architecture. We have R. Of course, that's what we are integrating with. Let's have a show of hands. Who ever heard of R language? Hey, we're seeing some hands here. Great, that's good, that's really great. Okay, and we have an object script API which we are using to connect to R, which is available for you on OpenExchange. You can just download it and use it. And most important of all, we have an interoperability adapter which you can use to automate and orchestrate your R processes right from InterSystems IRIS. So you have R, you have text to DAC, you have MLR, you have ggplot2. All the R libraries are available to you right from your InterSystems IRIS. Same for Python. We have pandas, Sklern, NumPy, TensorFlow. Who heard of TensorFlow? Raise your hands. Great. More hands. Awesome. Matplotlib. Yeah, Python. We have an object script API. We have an interoperability adapter. All these things, and I probably managed to show you what ML Toolkit is all about in less than 5 minutes, in 1 slide. You can get it on OpenExchange. In your events application, you have a PDF of this presentation. You can download it. It has all the links you'll ever need to get started. Try it.
little glitch. Thank you. Thank you, Edward. That was our deep tribute to Shiao-Bin.
Yeah. So our next steps and our findings from doing this, prototype. So doing this analog detection lab and examination records, we had, and doing this together, we found that we may be able to get more by using neural networks or neural nets like TensorFlow, but we were having trouble with how the data was presented for us to be able to do that. We're going to experiment more with text-to-vec, and maybe it could be a simpler approach to help confirm our algorithms that we're using. Fuzzy matching on more descriptions could secure a higher match. So we used like 1,200 new exams that needed to be mapped to, like, our gold standard is about 5,000 records. Some of the other things that we saw is that if we could pull out of the descriptions things like modality, body part, some things that are more deterministic, that we could categorize the exam code. That might help us to do more of the neural nets and using even the body parts, or even like the hierarchy of body parts, body systems, and that kind of stuff. So our next steps, we'll be testing with more data. Like I was saying, we actually have 50,000 mappings to our exam code record. We have those descriptions that come from our customers to map to those records. So we'll try to use those as to train the data better, or to test the data better, more better, there you go. Guessing the exam code mappings on the fly is really one of the things we want to do. So when the HL7 message comes in, we want to be able to guess what the new exam code maps to in the gold standard, so that our ED, ER exams can be better sent to the right subspecialist. And then trying other algorithms involving deep learning, and maybe introducing some other dictionaries, maybe like dictionaries of abbreviations, body system, body parts and subparts, synonyms, antonyms, and just stop words, or even like SNOMED or CPT codes. And then ultimately we want to reduce man hours by implementing machine learning methods and new exam code mapping dictionaries. And really in the future we see it working for other codes that we need to map. So this is just one instance of that.
Okay, thank you, Paul. Just before we pass to Q&A, just a couple of informational slides. Thank you. So first of all, as we mentioned, for those of us that would like to have a hands-on experience and have IRIS or Cache or Ensemble in their possession, those could refer to our OpenExchange marketplace, and there are two separate pages, one for the Python stack, and the package is called Python Gateway. For the R language, we have R Gateway. So there we can download the contents, import it into our installation, and here we go. The links to those pages are provided at the bottom of the slide. Those that are interested to do it in a collaborative way with the other customers and partners that already constitute a user group of Machine Learning Toolkit, please throw us a quick email to mltoolkit@intersystems.com. There is a private GitHub repo in our corporate GitHub farm that is serving that purpose. It actually implements that user group. For those that are fine with testing a smaller number of publicly available examples for Python only for the moment, we'll see how we go with R. There is a link at the very bottom, and there you may find a content for a couple of use cases that are publicly available. So that's the first thing. The second thing, before we switch to the Q&A mode, basically there's not much to announce here except for the artificial intelligence and machine learning symposium that would follow the main agenda of this summit. So please be welcome there. Otherwise, All the sessions that you see at that slide, they will be available as PDFs through the app and through the events website. So please refer to those resources in case you would like to have those slides for a quiet review. So with that, as we promised, we passed to Q&A, but we would like to do it in a creative way. How many time we have? We have 15 minutes, so we are quiet. So we could combine it with a demo of the functionality. So what we'll be doing, our suggestion is that I'll start showing and commenting on some of the mechanisms that we implemented for inland imaging live in the system. And as soon as some of you have questions, so please walk up to the microphone and just ask them. We'll stop, we'll respond to your question, and we'll resume the demo. Is that okay?
And he's going to start working on the demo, but I'll start fielding questions if you have any questions right now while he's bringing that up.
So first of all, there is an ARServe component. There is an R own application server, small application server that is being launched, and that one further passes all the callouts to specific packages. That's the specificity of the R gateway. So basically, what we start from a table from which I've deleted the results that are produced by a fuzzy join mapping method. We only have the results that are produced by the brute force method. So you have them here. For example, you have the similarity, but this is a brute force specific similarity going from 1 to 10 in our implementation. This is the code from the inland imaging's gold standard suggested by the brute force method, and that's the description of that test. These on the left are the exam descriptions and codes that are sent to us by inland imaging's partner. So those need to be mapped, and we're looking for the candidates using two methods, brute force and fuzzy join, to be considered maps to those codes. So fuzzy join is now deleted, and now we will reconstruct it first. So we'll rerun the fuzzy mapping process, and we'll also do the cross-method comparison using similarity and humanity metrics, using text-to-vec. So for fuzzy mapping, the process in our ensemble system, it looks like this. It's almost classical ensemble process, with one exception that you see above each of those bricks, you see a portion of, almost above every brick, you see a portion of the R code that corresponds to that step in the process. And for example, to start from, we need to load some packages into the R context using an ensemble activity. So what we do, we add that portion that calls in specific R packages into the R context. The other bricks that you see here may have a different function. For example, this one, it implements a query, SQL query, the result of which is then converted to a R data frame. That's an R specific object, almost a table, that R understands and R can analyze with its science packages. To further do our modeling, for example, to execution a portion of code that corresponds to data preparation, we just put it into this specific activity in our ensemble process, and it's being executed in the order that we regulate, using the flows and using the management elements of ensemble. Those could be loops if we want further robotize this process and make it work autonomously. We can use loops, we can use conditions, we can use anything we have at our hands in both ready-made form in ensemble or using object script as a method. So to show you, so basically what I do, I take this process in my production and just launch it. It takes several seconds to accomplish. That's take into account that we're working on a task involving about 4,000 records in the dictionary, and we have 100 non-mapped, and we have 1,200 mapped input records. So that gives you a space of approximately 5 million records to to work with. And given the, oh, that's finished. Given the task, it ran, say, reasonably well. What we receive is what we usually receive in Ensemble. We receive a visual log. The interesting part of that is that in that log we see the R content that have been sent to ARServe for execution. And in case we receive something back, we'll see what is being received. So let me check. Yeah, for example, the received mappings for non-mapped and for mapped by the humans input records. We will receive them back from the R context in our IRIS context as a text. So let's check what's happened to our table. So I re-execute the query, and yes, I'm getting here the results of the fuzzy join mapping. Any questions so far, gentlemen, ladies?
There you go. Use that.
Where is the R context running? Is that on the same instance as the IRIS platform?
So, yes, we are using the ARServe library. So it's like a TCP connection. It could be running on the same server. It could be running on a remote server. So you can choose the way you split the workload, whatever you want, on the same server. Separately, if there are some considerations if you want to pass a lot of data, but if you only want to pass comments, it doesn't really matter because the comments doesn't take that much space. Do you have any other questions?
Yes, we have still a couple of minutes. Well, let's finish the example and see maybe there may be more questions in the audience. So now we have two sets of results suggested by the brute force approach, brute force process. By the way, each of those methods are implemented as separate processes. You've seen it on the production, so that means they can be, I'll close that one. So that means they can work in parallel, independent from each other, or looking at the results of each other if needed, but here we don't do that. And we implement, as I said, we implemented a separate process to do the comparison. That one that is based on text-to-vec approach, on vectorizing the results that are produced by both brute force and fuzzy join. So again, it looks similar way. We have some tasks that are running in parallel, some tasks that are running sequentially. And in the end, we write the results back into a table in IRIS. And that last step is an object script. So let me around that one. Was short enough. So again, we have a nice visual log. We can at every step we can control what was sent, what was the result. And if we go to our table and re-execute, so we see that we have. Let me move that a bit to the right. We can see that a number of cross-methods metrics that we've presented on our slides have been calculated. So that. This is exactly, we're showing you exactly the genuine content that we implemented as a prototype for inland imaging, and I would be more than happy to work with the others that are interested to actually suggest something that represents your use case here. So please, any questions? We have several minutes. I will be happy to answer those. Sir.
It seems, so just to confirm, the same type of methodology could be applied to clinical terminology as well? I mean, here we're talking about test codes, but in HealthShare we have extensive data sources coming in CCDA format. We're dealing with SNOMED, and getting those to common terms has everything to do with deduplication and making that data usable for the physicians in the end. It seems like this would be able to be applied in the same type of context, that if you have a good mapping source to train off of, and you can find linear matches or vector-based matches, that you could probably do the same thing within the guts of HealthShare itself.
Yeah, and that's what we're looking to do in the future with inland imaging. This is like our prototype, but in the future we want to do most of our terminologies in that way. So we want to try to reduce the amount of work it takes to do those mappings and the human intervention of that. Yeah.
So I've been taking these classes from Andrew Ng with deep learning classes on Coursera, and this looks a whole lot like the recursive neural networks he does with text-to-vect for the neural translations. So what Google does with
it's close.
It's close.
It's close in the sense that before applying neural networks, you will do vectorization.
Right.
That's for sure. That vectorization will probably be a little bit more, will contain a bit more steps than we have here. You would, and then depending also on your setup, you might not be willing to work with your neural net because it's quite a calculation-intensive approach. With a whole lot of history that you have, I imagine you have like 10 years of mappings or history, or just 10 years of the files sent to you by your business partners. You would be willing to limit that scope, and then you'll have to work with, you'll have to portion your data and send them chunk by chunk into the neural net and see how it progresses. We are right at that moment. We are testing those approaches because they make more sense in a robotized implementation of an analytical process. But for the time being, since we are not yet fully exposed to the wealth of the data from inland imaging that exists, but we are not yet in contact with it. So we have suggested something that is, I'll say, budgetary variant of a neural net. But
Yeah.
you're right.
And David from their team is their data scientist, and he's been working on doing deep learning stuff with it. And that's where we were coming up with using SNOMED to help us map ours, and coming up with a dictionary so that we could get some more categorization from the description. That way we could apply the neural net to it a little bit easier if we had categories that we were working with, like modality and body part, laterality, those kind of things.
Right,
So.
right. So I mean, this is just kind of offhanded comment. I wonder if InterSystems could do something like a Kaggle where it's healthcare data centric and just give it to the community to try to find the best approaches.
We do have. Apologies, just a quick remark, and then I'll pass it to you. We have a number of use cases already published in the user community.
Okay.
Those we keep them in the private repo just because we want to know you and be sure that that once you start installing and using them, we could help you, and we just require simple personalization. Your GitHub account, that's it. We have full documentation that is available in the user group, which is an illustrated manual for both Python and the R sides of ML Toolkit. So please be welcome. Plus, since you've touched the neural net specifics, we will be running a webinar probably in October, and we'll be after that webinar we'll publish a use case publicly available through the user group. That would implement a neural net that is trained in portions, so not the whole lot like it's done in a lab design, in a, so to speak, in a data scientist's world, but it will be fed with portions of data that are arriving like in the real world setup. So that will be interesting. Please consider joining the user group, and you'll have it.
Okay. Okay. Thank you.
Okay, so.
Yeah, we're pretty much done, I guess. So
I think we are at the end. We are really at the end of the hour. We thank you very much for your participation. Stay with us. Join the user group and use ML Toolkit.